Hi everyone, it's been a while since I wanted to make this video. Today I want to talk about language models, specifically how to train them. I want to spell out the whole process, including how to find a dataset, how to pre-process it to train a language model on it, and what does it mean to train a language model, and what is a language model itself. I want to answer all these questions and I will show you the code to implement the training process. Actually, I have already implemented this and you can see this library called LLMTrainer. You can install it with a package manager pip, with the command pip install LLMTrainer. And let's see 5 lines of code which show you from a very high perspective how you can use this library. But this library is very simple. All you need to do is create a dataset. Create dataset is a function implemented within this library. It will generate the default find web dataset. We will speak about this dataset a bit later. Then you define your model. You can use any model, GPT, xLSTM, or state space model, whatever you want. It should be a language model. Then you define a trainer and start training. Simple as that. The LLMTrainer has a lot of parameters, but they have their default values, and the method train has a lot of parameters, but they also have their kind of a good default values. So you might define your model and start training with these 5 lines of code. That's it. Default values for all the parameters are overall good, so you can just define your model and start training. But if you want to change the learning rate, the schedule, the optimizer, or something else, then it's fine, you can do it with this library. But before it, let's start with how to prepare a dataset. The first step is to find a lot of text. You can do it by yourself. You will need to parse many websites from the internet, but it's a very tedious process because you need to parse raw HTML files, and also there are many garbage websites which you don't want to show to your model because it's not useful. You want to show your model some educational content, a content that contains some knowledge. And there are some datasets that are already collected and you can use them to train a language model. One such dataset is called FindWeb. You can read a whole article about this dataset, how it was collected, which filters were applied, and so on and so forth. But for this video, you need to understand one thing. This is a dataset which contains lots of documents. Each document is a plain text. Plain text is what you need to train a language model, because this is how language models are trained. The first step of training is so-called pre-training. Pre-training is when you show your model the whole internet. You show it a plain text and the model understands something about the world in general. You show some text about physics, some text about chemistry, and so on and so forth. So this FindWeb dataset provides a lot of text, and the first step is done. Find a text corpus. Now we have it. You can download this dataset and I will show it in a bit. The second step is tokenize the text. What does it mean to tokenize the text, and what a tokenizer is, and why do we need this? Well, a language model is a neural network. It solves the problem called next token prediction. You have some sentence, for example, I am from, and you want to predict the next word. And this is what a language model performs. It predicts the next word, actually predicts the next token, which we'll see later. But now this is how you should treat a language model. It predicts the next word given a sentence. And a neural network doesn't know how to operate with a raw text. It knows how to operate with numbers. So we need to represent the text as a list or as an array of numbers. This is done by using a tokenizer. Let's have a look at one tokenizer. You can enter some text, for example, hello, I am from something, 3 dots. And you can see that this text is now split into substrings, and each substring, for example, hello, has its own token ID, and this text is now represented as 5 integer numbers. You can continue typing, for example, and I am very interested in AI. And you can open text and see how this text is split now. You see that space interested is a single token, space varies a single token, and so on and so forth. You might ask me, but how tokenizers understand how to split the text? Well, it's actually a very simple process. It's called, at least you can build tokenizers in different ways, but one popular way to build a tokenizer is called byte pair encoding. This is a straightforward process. You start with a vocabulary that consists of single characters. For example, character A has its own token, which is 64. A character U has its own token, which is 84. A token dot has its own token with a 13, so on and so forth. And then you build the vocabulary. You build it by a natural process. You look at your text and you find a very frequent combination of characters. For example, A or CE. This combination of characters is very frequent in your dataset, and you want to add a separate token for this combination. CEL is also very frequent, and you add a separate token for this combination, but CELZ is not popular, and you can see that this sequence is represented as a list of 2 tokens because it's not frequent, it's not popular. And you continue adding new tokens until you have a decent number of tokens in your vocabulary. A decent number is about 50,000 or 100,000, 200,000, something like this. You don't want to build a very huge vocabulary because it will be computationally intensive or even computationally impossible to build a model. All right, I think we're done with the second step, which is tokenize the text. So first step was to collect a lot of text. The second step is apply a tokenizer to represent your text as a list of numbers. The last step is very simple. You need to save the tokens. I specify some details that, for example, how to save them. You need to use a NumPy library, but these are the implementation details. I think this is basically it. This process is done by a function called createDataset. I think that we shall proceed to exploring the code of creating a dataset. I haven't yet said anything about the library itself, so let's have a first look at the library. LLMTrainer has 2 subdirectories, dataset and trainer. Trainer is responsible for the training process. For the optimization process, let's keep it for later. The one that we are interested in right now is a dataset. It has 2 files, DataLoader. DataLoader is the class that we are going to use during the training. But now let's focus on the first one, createDataset. CreateDataset is a file with only one function, createDataset. It's a very simple function. Let's first look at its parameters. It has 4 parameters. Save directory is a directory where you want to save the files. Dataset is the name of the dataset that you want to download. Now I only support only one dataset, which is Fine Web Educational. 10B stands for 10 billion. 10 billion tokens. You can download more, like 100 or 350 billion. The next parameter is chunks limit, how many files you want to download, and chunk size is how many tokens there will be in each file. So in this case, I want to download 1.5 thousand files, each of 1 million tokens. So it will be 1.5 billion tokens in total. And the code of this function is pretty much simple. Let me give you a brief overview of this. I downloaded the dataset. It happens here. Dataset equals load dataset. Load dataset is the function from a library datasets, and when I download this dataset, I specify a path on Hugging Face, the name of the dataset, the split, and it's important to set streaming equals true because by default streaming equals false, and streaming is responsible for how you want to download this dataset. Do you want to download it at once? But this dataset is very large, and at least I didn't manage to download this dataset at once because I don't have so much memory, and to avoid troubles related to the memory of the computer, I set streaming equals true. This way it doesn't download the whole dataset, but it will download it in chunks, which I do right here. I iterate over the dataset. Dataset is an iterator, so you can iterate over it, and I apply tokenize to every document from this dataset. Tokenize is a simple function which tokenizes the text, and it concatenates tokens of the document with a special token called end of text token. End of text token is a special token. It looks like this, and the value of this token is for this tokenizer. It's a tokenizer used for GPT-2. So the value of end of text token for the tokenizer used for training a GPT-2 model is 50,256. And end of text token is used as a delimiter between documents. When you have many documents, you want to say to the model, hey, these documents are different, they are not about the same topic, and you put a delimiter between these documents, a delimiter called end of text. I think it's all you should know about this code because it doesn't do anything clever. So to recap, you download some dataset, you iterate over documents, you tokenize each document, and you add end of text token after each document. And you save the tokens. Let me show you how to save the tokens. For this, I use numpy.save. I specify the file name and the tokens themselves. That's it. Let's see how this function works in action. I also have a file called example GPT. It's a Jupyter notebook which shows how to use the library. And the first cell is about creating a dataset. And let's run this cell and see how this function works. I specify save directory equals data, so I expect my files to be downloaded to this directory. Then I'm downloading a dataset file web educational. I specify chunks limit to 50. That is, I want to download only 50 files, and each file will contain 1 million tokens. Now we can see that the files were resolved, and now we are processing the chunks. It takes a while because you need to connect to the dataset on Hugging Face to resolve the files and then download them one by one. Alright, the files were downloaded, and now we can see this data directory, which contains exactly 50 NPY files. The second file from this dataset directory that we should talk about is called DataLoader. DataLoader is what you always use when you train a neural network, because you don't want to optimize your whole neural network based on the whole dataset. You consider just a subset of the whole dataset, and you optimize the weights of the model based only on a few samples. And this is how DataLoader works. You load a batch of data, you feed forward this batch of data to your neural network, you calculate the loss, you do the backward pass, during backward pass you calculate the gradients, and based on the gradients you perform the optimization step. The only thing I want to talk about regarding this file is what are the inputs and targets here. First, I must say that there are different strategies how you train a language model. There is a strategy called masked language learning. You take a sequence of tokens and you randomly mask some tokens. But in this case, I don't use this strategy. I use another strategy called next token prediction. And first, let me show you an example of how it works. Here I have some sentence. I'm a large language model designed to help people. And here's a representation of this sentence using some tokenizer. And the way you build inputs and targets, first you need to fix the context window, say context window equals 4, context window is how many tokens in your sequences. We consider the first 4 tokens and say this is our input. So input 0 is the first 4 tokens, and we construct the target by shifting these 4 tokens by 1. So we consider the next 4 tokens and we say it is our first target. Target 0 equals this sequence of tokens. And you can see that these 3 tokens are shared. So the task is to predict the next token. This is what our language model learns. And we take this window of 4 tokens and we go through this sequence and create these input target pairs. But notice that for the last 4 tokens, we don't have the next token, so we cannot create a target for the last input. For this reason, if you look at the code, I don't consider the last token because there is no target sequence for that. And this is how inputs and targets are created. You take a one-dimensional sequence of tokens, because remember what's inside our files that we just created in this data directory. This is one-dimensional array of tokens. And you take this one-dimensional array and you reshape it into two-dimensional array, where the first dimension is a batch size and the second dimension is a context window. So this is how we create inputs. Just use this view method to reshape this one-dimensional array into two-dimensional array. And then you do the same with targets, but you shift all the tokens by 1. That's it. I hope that now you understand how it works. And also, let me show you that another approach that I mentioned called masked token prediction. In this case, you take the input sequence and it becomes our target sequence. And for our input sequence, you take the target, call it our input, and you randomly choose some token, say this token, and you change it to another token, a special token. We introduce a new token. Remember, we already have a token called end of text. We used it as a delimiter between documents, and now we just introduce another special token called masked. We will come up with some value for this token as well, say 50,257. And this is how it works. You take your tokenizer and you add a new special token to the vocabulary, and you say this is a masked token. So the problem that a language model will learn to solve here is to understand what the original token was there. Sometimes you don't mask any token, and the language model should understand that the sentence is already good and it doesn't need to change any token. Alright, I think this is all I wanted to say about DataLoader, and now we can finally open a file LLMTrainer and explore the training loop. LLMTrainer is the main class that you use to train a language model in LLMTrainer library. And it has some parameters. The first one is model. You must specify your model, a model you want to train. And all other parameters are optional, like optimizer, scheduler, tokenizer, end of text token. You can stick to the default values. They are none, but they will be changed to their default configurations. And if you want to change the optimizer, you can create your own one, then you create a scheduler and pass them to this LLMTrainer object. The only important function here is this train method. Train is what you call to start training. It takes many parameters. Let's go through them one by one. The first one is max steps, how many steps you want to perform. The second one is save each n steps, how often you want to save your model, save the checkpoints, and then how often you want to log the training information. And the first important parameter is batch size. Batch size is how many sequences you want to process during one optimization step. And you should be careful with this number because you cannot set this number to be very low. Because if it's a low number, then the model will use only a few sequences to perform an optimization step. But it's a bit silly to optimize the whole network based on a few sequences of tokens, you want to consider many tokens, like at least 100,000 tokens, and based on them, perform an optimization step. So you calculate kind of the average gradient and you perform an accurate step. But it's better to talk about not only a batch size, but a pair of batch size and a context window, because how many tokens you process per batch is defined by a product of batch size and a context window. For example, you have a context window equals 100 and a batch size equals 10. 10 sequences, each of 100 tokens. In total, you will process 1000 tokens per batch. And generally, you want to process at least 100,000 tokens per batch. The second parameter is called a mini batch size. The problem is that you cannot increase a batch size a lot because it will not fit into your memory. Primarily, I'm talking about GPU memory. If you want to train your model using a video card, then you will send the data to GPU memory. And if your batch size is very high, then it will not fit into GPU memory. And people address this issue by a very popular and common trick called gradient accumulation. Let's explore this trick in code. It happens here. For each step, for each optimization step, I perform many steps. To be more precise, gradient accumulation steps. Gradient accumulation steps is a number such that you multiply it by a mini batch size and you get a batch size. So gradient accumulation steps is a batch size over mini batch size. And for each of these so-called mini step, you load a new batch, you calculate the logits, you calculate the loss, you do the backward pass, but notice that you don't perform the optimizer step. It happens out of the loop. So during this loop, you only load a batch, you perform a backward pass, but you don't do the optimization step. You accumulate the gradients, and then after gradient accumulation steps, you perform one optimization step. This is called gradient accumulation. I hope it is clear now. And let's go back to the parameters. There are some more to cover. A context window, again, is the number of tokens in each sequence. Data directory is where our data is. And you can remember that I saved all the files to this data directory. Also, there is a logging file where you want to save the information during the training process, logging information, how often you want to generate some text from your model. When you train a language model, it is important to look at a couple of things. The first one is the value of loss. You want your loss to decrease. If the loss function does not decrease, then something is wrong. You should increase the batch size, for example, or tweak the learning rate, play with the optimizer, scheduler. And the second thing you want to look at is what your model actually produces. And you give it a prompt. For example, in this case, a default prompt is once upon a time, and the model is asked to continue this sequence. This text will be represented as a sequence of tokens. Then the model will be asked to continue this sequence. It will generate 30 or 50 tokens, and then you decode the sequence of tokens back to the text, and you see what your model generates. All right, let's look a bit more at the training process. There are some things that are very technical, creating a directory for the checkpoints, or the logging, creating a data loader, and so on and so forth. But there are some things that I want to point out. For example, this torch compile function. This is what you should use by default when you train a language model. Torch compile will kind of forget about Python interpreter, and it will compile your model, the forward pass, and it will try to optimize it. So it will take some time because compilation takes some time, but then it will speed up the training process a lot. So I highly recommend you to use this compile function. Also, there is another trick. When you train a language model, you usually can afford to use a lower precision to again speed up the training process. And to this end, people usually use so-called bfloat16. Don't use float16 because float16 represents only a limited range of numbers, and you will need to use something called gradient rescaling. It's getting a bit messy, and if you don't want to deal with that, just use bfloat16. It represents a wider range of numbers. It is less precise, but it's fine to train a model using this data type. Also, I clip the gradient norm. If the gradients are very high, if their norm is more than 1, I clip it. So I make sure that all the steps are relatively slow. And then sometimes I sample from the model, I save the model, I perform logging, and sometimes I print the train information like step, loss, norm, learning rate, and other information. It's not that interesting. And other than this train function, there are some auxiliary functions, for example, generate text, or save checkpoint, load checkpoint, configuring default optimizer, configuring a default scheduler. I think they are of no interest in this video because the main topic is training a language model, but these are all about classic deep learning stuff. The only thing I want to mention is how you generate from your model. There are different ways how you can sample from your model, how you can generate a text. One popular way is called the beam search, but in this code I used a different approach called top case sampling. Top case sampling is a very straightforward process. You have a sequence of tokens, then you want to predict the next one. When you predict the next token, you actually calculate the logits. It is the output of a language model, and you apply softmax, you get a probability distribution over all the tokens from the vocabulary. That is, you have, for example, 50,000 tokens in your vocabulary, and you predict the probability of each token from your vocabulary to be the next one. You have a sequence, and you have probabilities for each token to be the continuation of this sequence. And you keep only k tokens out of 50,000. You have 50,000 tokens in your vocabulary, and you keep only k out of these 50,000, top k with the highest probabilities to be the next one. And then you sample from those 10 tokens. You have 10 tokens, you have assigned probabilities to them, and you can sample from this distribution. This is a so-called multinomial distribution, and this is how this function generate text is implemented. Also, it has a parameter and return sequences, how many times you want to sample from your model. You give it a single prompt, but then you sample from it and return sequences times, and each time you end up having a different result. Well, now I think that's it for this code, but if you have any questions, of course, feel free to ask them. And now let's go back to this example GPT Jupyter Notebook. Actually, I want to open it on GitHub page. Now let's open it and see how I train a GPT-2 model. Here I define this model. I imported GPT-2 from Transformers library. I also import tick token to initialize this GPT-2 tokenizer. And then I create an LLMTrainer object, which we just have seen, and then I start training. After we start training, you will see the output. I set print logs each n steps equals 10. So after each 10 steps, I see the output, the step, the loss, the norm, and so on. And after 100 steps, I set generate each n steps equals 100. After 100 steps, I see the output. So let's have a look at this. The prompt was once upon a time in Russia. Once upon a time in Russia, of the first the number of the U of order to look. We can see that this text is very incoherent, but you cannot expect anything else because the model is not trained. We waited only 100 steps. Let's look the output after 1000 steps. Once upon a time in Russia, the Germans arrived in a single at the center of the city where about 20 yards were to run at the same time. Once upon a time in Russia, it took place. There would be any sort of one man or man of slavery. There was one man named John. Once upon a time in Russia, we were able to learn about different ways of copying the war and find an active role in the military action. You can see that this text is much more coherent, but it still requires much more time to optimize the whole neural network. And also, I wanted to show you that it only has 51 million parameters, which is a very small number. You should consider at least 100 million parameters if you want to train a language model. And also there are some plots which I want to show you. For example, this is our loss function, and you can see that it decreases steadily, and you definitely can continue training this model. The loss will decrease and the output should be much better. Also there is a learning rate and a gradient norm which look awesome. There are a few more things that I want to cover. The first one is another example. Here I trained another model. I trained an xLSTM model. xLSTM is an architecture that was introduced a year ago in 2024, and it's an improved version of LSTM, but it still remains to be seen if it can be a decent competitor to the transformer architecture. But it's still fun to train this model and see its performance. I trained a small version with 125 million parameters. It is 1 million parameters less than a small version of GPT-2 model. Then we can create a trainer object. I am already done with the training process, but I want to use this LLMTrainer to sample from the model. Remember, during training, if you call trainer.train, you see there is one parameter called savedir. It is the directory to save the model checkpoints. And I have a directory checkpoints which has one file. It is a checkpoint of the model which was trained for 5,000 steps. And when you're training your model, you want to sometimes save it so that after the training you will load your model and see its performance. This is what I want to do now. I can load the checkpoint. For this, LLMTrainer has another function called load checkpoint, which takes one argument, a path to your model, and when you run this, your LLMTrainer object which loads the model state, and then you can generate some text using your trained model. Generate text has 3 parameters. Length is how many tokens your model will generate, and the last parameter, and return sequences, is how many times you want to continue this sentence. Let's say I want to continue this sentence 3 times and run this code. Now we can see 3 different continuations of this prompt. Let's have a look at them. Once upon a time, the world had no time or a place for anything, but the sun never set and the sun never came to an end. Sounds kind of poetic. The next sample, once upon a time, people started to think of the earth as a body of water. When they saw the earth, so you can see that the output of this model is really coherent. And if you want some strict evaluation of this model to understand how good it is, you can use different benchmarks. I actually evaluated this model, and it is still worse than a small version of GPT-2 model, but it was trained on 1.5 billion tokens, whereas GPT-2 was trained on 100 billion tokens. So maybe I can continue the training process and the model will improve. Anyway, I wanted to show you that you can train any language model and then load it and see what this model can generate. But now all it does is continues a given prompt. It is called a base model. It is a model that contains some general knowledge of the world. If you want to train an assistant model like ChatGPT, you will need to perform another step of training called supervised fine-tuning. SFT is in essence the same process, and you can do SFT using this LLMTrainer library. The only thing that you should change is the vocabulary of your tokenizer and the dataset. You need to train your model on dialogues between assistant and user, and you will need to introduce new special tokens for a user and an assistant. But I must say that You cannot train an assistant model with such a small number of parameters. You will need at least a couple of billion parameters to train a language model that can answer questions. I hope this video was helpful. If so, give it a like, write a comment, ask me some questions, and if you want to contribute to the LLMTrainer library, feel free to do so. Just create a pull request and I will review it and merge to the main branch. Have a good day.